Hello everyone, and welcome to the companion video on vectors. Now, here's how this is going to work. I'm going to have in the video description a list of video times for various different topics I'm going to discuss. Like, first off, I'm going to discuss what a vector is, in case you don't know. Then I'm going to discuss how all the different operations work, like length and normalization. And then at the very end, I'm going to discuss how all that works in terms of game development. So with all that out of the way, let's go ahead and get started. So, first off, for those of you who are unfamiliar, what is a vector? Well, a vector, first and foremost, it's a number. You can represent things with it just like you'd represent things with any other number. You can have a vector equal to 10 or 20 or negative 578 or whatever you want. The key thing that a vector adds to numbers that makes it different is that number can also have a direction. So I don't have to just have 20. I can have 20 in directly up, or 20 going at a 47.8 degree angle. And that's really what a vector is. So, for example, the way the vector does this is, first off, I have an x and y axis like this. And let's say this is my vector. The way I represent the vector is I represent how far I go across in the x-coordinate, and how far I go up in the y-coordinate. And that's how I represent length and direction with a vector. That, by definition, is what a vector is. So, yeah, it's just some amount in a direction represented with some amount in x and some amount in y. If you want more in-depth explanation than that, you can go and look at some other math videos. I'm sure they have it. This is really about vectors in context of game development. So if you want more information, look there. Moving on. So next thing I'm going to talk about is vector length. Now, as I said earlier, a vector is just some amount in the direction. And you'll use the length function if you want to know how much that number is and don't really care about the direction. So for example, right here, as you can see, I have a very distinct amount right here. I'll call that amount L. But I'm not representing the vector with this amount. I'm representing it with some amount in x and some amount in y, an x and y coordinate essentially. So how do we get the length? Well, the solution is actually not that hard. You just pretend that it's a triangle, and x is sort of like the base of the triangle, and y is sort of like the height of the triangle. And you treat it like you're solving for the hypotenuse, as L is a hypotenuse. So, by that, then L would equal, oh dear, L would equal x squared plus y squared, and it would equal the square root of that by the Pythagorean theorem. And that's where the whole length thing comes from. And again, where would you use that? If you want to know how long the vector is, how big the number is, but don't really care about what direction it's in. So, next up is vector arithmetic. How do I take a thing like, say, a, and the notation for vector is you take the variable and you put like a little arrow above it that denotes it's a vector. So I have a. How do I calculate, say, a plus b? How do I add them? How do I subtract them? How do I multiply? How do I divide? And this is, again, not that difficult. Here's the thing. The entire vector is represented by some amount in x and some amount in y. So if I do the same thing to both of these components, it's equivalent to doing whatever that thing is to the entire vector, since I've done it to everything that composes it. So all I have to do to say add them is take x, well, I should say take a, the x component of a, and the x component of b, and then take the y component of a and the y component of b, and these two are essentially equal. So this equals this. And that works for all the operations. This is the same thing for subtraction, multiplication, and division, because, hey, if I do the same thing to every piece of it, then it's the same thing as doing that to the whole thing. Next thing is normalization. What does it mean to normalize a vector? Well, it actually means something pretty simple. It just means, hey, take this L thing and set L equal to 1. So you might be wondering, well, how on earth do I get the vector length to be 1? Well, the normalization system says it's pretty easy. L must equal whatever the length is now divided by whatever the length is now. And of course, you know that by definition, anything divided by itself equals 1. So now the only other question that might remain is, well, how do I divide an entire vector by L? Well, the neat thing is, since the entire vector is essentially the sum of these two components, well, I guess I don't want to say the sum, because that has a mathematical definition, but you get the idea. The whole vector is represented by those components. So if I divide both of those components by the same number, it's equivalent to dividing the entire vector by that number. So, since I'm not interacting with the length directly, I take x, and I divide that by the length, and then I take y and divide that by the length. And effectively, that normalizes a vector because it takes the whole thing, the length, and divides it by itself. Length divided by length equals 1. And that's vector normalization. There's not that much to it. Okay, so next up is the dot product. Now, all the dot product is its multiplication between two vectors. But what makes a dot product different from just regular multiplication is it takes into account the direction. So for example, let's say that vector A here, that's some minecart. It's on some track in, of course, that direction. And let's say vector B is me. That's not only how much I'm pushing the minecart, but the direction I'm pushing it in. What the dot product would effectively calculate is how much I'm pushing the minecart along the original track. Because, I mean, if I'm pushing it this way, you know, the amount I'm pushing, like, this direction, for instance, that would have no effect whatsoever on the minecart's movement in that direction. So that's what the dot product does. It takes into account, hey, you know, I'm not pushing the minecart head on. I'm pushing it at like a little bit of an angle. So I can calculate how much I'm affecting, taking into account that angle. And so therefore, the dot product is A, some vector A, dot, some vector B, and it equals the length of vector A times the length of vector B times the cosine of whatever angle is in between them. So essentially, this angle right here. And that's the dot product. That's how it takes into account, hey, you know, it's not entirely head-on. And the reason it's cosine is because, well, if cosine is 1, that's when the vectors are going directly along the same direction. So it would just be straight-on multiplication then. I'd be getting the full effect if I'm pushing the minecart from behind. But if the vector's going in this direction, if it's perpendicular, then cosine 0. It would have no effect, because I mean, if I'm pushing the minecart on the side, that has no effect on making the minecart move forward. And again, that's just an example to help you visualize it. But another way you can look at the dot product is piece by piece. I could say, hey, this is also equal to how much I'm pushing the minecart A, how much minecart's directional direction, times how much I'm pushing it in that direction, plus the minecart's original direction in Y, times how much I'm pushing it in Y. That's another way of looking at it, and these two equations are entirely equal. They mean exactly the same thing. And, in essence, that is the dot product. Okay, next up is the cross product. And what the cross product does isn't really that hard to understand, hopefully. Here's how I like to visualize it. Take your right hand and just put it out in a fist. Now, point your pointer finger directly out. Now point your middle finger out sort of like towards your left hand. It's like a perpendicular 90-degree angle to your pointer finger. Now point your thumb directly up. And you should end up with, well, it's kind of hard to describe, but you should get the idea. Now if you treat your pointer finger as the first vector, and your middle finger as the second vector, then your thumb is a cross product. It's the vector that's completely perpendicular to two other vectors. And yeah, that's the cross product. So, if you take, for example, like this example I've drawn out right here, the x vector and the y vector in the x and y dimension, then the x-axis cross the y-axis is a z-axis, and that's sort of where you can get 3 dimensions from. And yeah, so the idea isn't too overwhelming, but the real challenge really comes from the math of getting all this to work. Okay, so to show you sort of the math that goes behind this, I'm going to define a few vectors. I hat is 1 unit in the x-axis, j hat a vector that's 1 unit in the y-axis, and k hat is a vector that's 1 unit in the z-axis. And I'm going to sort of use these to help illustrate the cross product. Now, first off, there's a few things that you might get pretty much off the bat. Like, for example, where should I put this? I'll just scroll over a bit and put this right here. K hat, for example, would be the cross product between I hat and j hat. Because, you know, based on the thing I just showed you, x-axis cross y-axis equals z-axis. But there's also another way you could do this. What if I did this calculation in reverse? What if I did j hat cross I hat? Well, that would be almost the same thing. It would give me something in the same axis. It would just give me, you know, negative. So that would equal actually negative k hat in the other direction. But just to keep this all in the same equation, I'm going to redefine that as negative j hat cross I hat. And the same thing, I've just moved the negative sign from k hat to the j. It gets the same thing in the end. But the whole point of this is there's a few cross products which we already know sort of intuitively. Like that's k hat. J hat would be the x-axis, if I can actually write this out, I hat cross k hat, if I, again, can write it out. There we go. Or I can, again, reverse that and do negative, come on, there we go, negative k hat cross I hat. And I'll just do the last one off screen. Okay, and I just did the same thing for I hat. And I also reversed the 2 equations on j hat because I realized I actually wrote them backwards. I'm sorry. K hat cross I hat gives j hat. I hat cross k hat gets negative j hat. So, sorry about that. Off by 1. Common logic error. But yeah, these are sort of the easy cross products. You know, if you cross one axis with the other, you get a third axis. The question is, how do you do this with any arbitrary 2 vectors? And this is why I've wrote out this sort of matrix right here. It's going to help do that. Because one way to look at vector operations, like we've seen in the past, is just piece by piece. So if I have some arbitrary vector, a hat, and I want to cross it with some arbitrary vector, b hat, I can just do that whole thing piece by piece. So ax times bx, because it's a multiplication operation, times, and since these are the x-axis, I'll multiply by the x vector. So I hat cross I hat. And then I can add that to ax times by times the respective axial sort of vector effect. The unit vectors, if you want to call them that. So I hat cross j hat. Then I can add that to the effect of ax times bz times the effect of those unit vectors, so I hat cross k hat. And yeah, just write this out, keep adding on for all 9 of them, which I'm also going to do off screen, so one moment. Okay, I finished writing out the giant monstrous equation for the cross product, but before I go into that, I just want to talk about one more thing really quick. if you have a vector and you cross it with itself, it must be equal to 0. Why? Because of this thing right here. According to all these equalities we've done here, some vector crossed with another vector must be equal to negative the other vector crossed that vector. So, or in other terms, A cross A must be equal to negative A cross A. But what value could you possibly have in that equation where that would still hold true other than 0? If you had any other case, then the negative value must be equal to the positive value, and the only number where the negative version is equal to the positive version is 0. So therefore, any vector crossed with itself must be equal to 0. So now we can finally simplify this monster equation into the more simple version of the cross product that I used in the code. First off, I have 3 instances where I'm crossing some axis with itself. So all these terms effectively are 0. I can just get rid of them because, well, any axis crossed with itself must be equal to 0. So now that gets me ax times by plus whatever I hat crossed with j hat is. Well, what is I hat crossed with j hat? Right here I say I hat crossed with j hat equals k hat. So I'll take k hat times a hat x plus by. Well, ax times by, excuse me. And that's my first term of the equation. K hat times ax times by. But you'll notice that there's another thing that equals k hat. Negative j hat times I hat. And I have j hat times, or j hat cross I hat here. So ay times bx times negative k hat. Well, if I just factor that around, that means that's ay times bx times k hat. But wait, negative ay times bx times k hat. There we go. So what I'm going to do is I'm just going to do that whole thing in one here. I'm going to subtract ay times bx and factor out the k hat. Because if I distribute this k hat, I end up with the same 2 terms. ax times by times k hat, which is equal to this term right here, and negative ay times bx, which is equal to this term right here. I'm just sort of skipping a step here. I hope that doesn't confuse you too much. And that gets me the k hat effect, or this is the amount on the z-axis. So, if I go down a bit, next up I have, which one should I do next? Should I do, it really doesn't matter, but, oh, I'll do I hat next, why not? So, I hat, first term I want to look out for is j hat cross k hat, which is right here. So, I hat times ay bz, and then I have the term in reverse somewhere, don't I? K hat cross j hat, right here. But I'm going to do the same thing and replace that and distribute the negative, so subtract az and by. And that gets me, whoops, the cross product on the x-axis, effectively. And finally, of course, there's j hat, which, if I do that whole giant equation thing again, k hat cross with I hat, so first time that's there is there, so I can replace the k hat cross I hat with j hat, az, bx, and the only remaining term is this one, ax bz, which is I hat cross k hat, and I hat cross k hat is negative j hat. So I'm going to keep the negative with the term ax, ax bz, and just distribute out, or factor out, the j hat. And that gets the y effect, how it affects on the y-axis. And really, since these unit vectors right here represent the axis, I can effectively just get rid of them and say that these all equal the x, y, and z components of the final vector. So there you go. That's the cross product equation for arbitrary vectors. I know, it's big and complicated, but don't worry. One final thing I'd like to talk about before I move on from the cross product is the length. Because if I calculate out the length, and after all this math, I'm not going to bother. I know Khan Academy has a video where they prove this, but just take my word for it for now. If you measure out the length of the cross product vector for this giant equation, the length is proportional to, so the length of a hat cross b hat is equal to the length of A times the length of B. Well, first off, times whatever the perpendicular vector is, so n, times the sine of, dang it, this is sine of the angle between A hat and B hat. There you go. And you notice that corresponds really nicely with the dot product, which takes A hat times B hat times cosine of angle. So that's sort of the really cool thing about the dot and cross product. They can be used to get sine and cosine pretty easily. And yeah, that's all I really want to talk about for the cross product. So that just leaves the vector rotation for 2 dimensions. 3 dimensions is something I'm going to cover much later. And then I'm going to go ahead and move on to how all this stuff is used in the context of game development. So, one moment. And the final vector operation I'm going to talk about is rotating a 2D vector. Because rotating 3D vectors gets really weird, so I'm not going to talk about that for now. But to do that, I'm going to revisit our good old friend, the complex number. Because you might notice complex numbers and 2D vectors are incredibly similar. I mean, what's a 2D vector? It represents some amount in some direction by giving some amount on the x-axis and some amount on the y-axis. What's a complex number? Well, it represents some amount in some direction by representing some amount on the real axis and some amount on the imaginary axis. And that makes it a really, really good tool for converting vectors over. But why on earth would we want to convert vectors to complex numbers? I mean, sure, they're similar, but what's the benefit? And the answer is very simple: the imaginary number. What is the imaginary number? That is really the heart of this problem, and ultimately the answer. All the imaginary number is it's one unit in some different dimension. So not whatever your real dimension is. So in our vector case, that could be our y-axis. Hint, it will be. But the point is, that's all the imaginary number is, one unit in a different dimension. And the benefit to that is, when you multiply by this one unit in a different dimension, the imaginary number, all you'll do is you'll take your number and you'll rotate it by 90 degrees towards that separate imaginary dimension. And that is why complex numbers are going to be so useful for rotation, because all rotating by 90 degrees at least takes is multiplying by the imaginary number. And that is why you want to convert temporarily your vector to a complex number. If you take advantage of this, you get the really interesting effect of complex numbers. If you multiply a complex number by another complex number, what you get is not what you might expect from multiplication if you're used to vectors. What you get is a rotation. It will take the first complex number and it will rotate it by whatever angle, this angle right here, the second complex number represents. And that is all due to the inherent rotational property of the imaginary number. That is why it's so critical to convert it over in order to make rotation easy. So now that I've covered all that, hopefully that makes some sense to you as to why we're converting it over to an imaginary or complex number. This is the equation system. We have our imaginary complex number, our first complex number, and our second complex number. Our second complex number is just constructed from the angles. I'll go over that really quick in a bit. but you have these two complex numbers. One represents our original vector, the other represents the angle we want to rotate by. So what we do is we multiply them. Remember how to multiply complex numbers? You essentially do I believe they call it FOIL in math class. So term 1 times term 2, then plus term 1 times that term, plus this term times that term, plus this term times that term. And if you do that, you get y1 times y2. Imaginary numbers multiply. They do full 180-degree rotation, because what's two 90-degree rotations? 180 degrees. And where does 180 degrees rotation end you up around the real axis? Well, 1 unit in the other direction, so negative. So fun fact of the day. I don't even know why I bothered explaining that, but yeah. That's why I times I is -1. It's a 180-degree rotation. But anyways, not what I'm trying to cover here. Don't know why I brought that up. So, I times I, negative that, so you get negative that plus y1, imaginary, times x2, so that term, plus x1 times that y, imaginary, so that term, plus that term. And you can rearrange that to be like this. x1 times x2 minus y1 times y2 plus x1 times y2 plus y1 times x2, all imaginary. And that right there is essentially the key to rotation. That's where the whole rotation thing comes from. At this point, you can stop treating it as an imaginary number anymore. The imaginary part has served its purpose. But it's performed the rotation, and that's all that you really care about. So now, the only question that might be remaining is, how do you get the angle? Where does the angle come from? That is where sine and cosine come into play. I have some angle, but I don't have vector components for it. I do have this fun thing from trigonometry called the unit circle, though. If I can actually draw anything that remotely looks like a circle. There you go. So I have this angle, some angle, and what does sine get you? Sine gets you the y amount on this circle, cosine gets you the x amount on the circle. And if you combine them together, it gets you some point on the circle, which if you treat as a vector, gets you gets you one line to 1 unit on the unit circle, which if you treat as a complex number, gets you that original angle in complex number form. There you go. That's where that comes from. Hopefully that makes some sense to you. If you haven't taken trigonometry, you may have some difficulty. But if I just go back to the code really quick, you'll see that's exactly what it does. It takes, first off, the cosine and sine to get that second vector, and then it just straight up performs this calculation right here. The whole complex number thing. That's where that equation comes from, and all we do here is we implement it. So x times the second one, which is cosine, y times the second y, which is sine, and then it subtracts them, just like right here. For our y component, takes x times the sine plus y times the cosine, which is exactly what it says here. X times the y component of the second vector plus y times the x component of the second vector. If my voice will actually work. Whew. And with all that out of the way, you'll see that's exactly what that does. That is how the whole 2D vector rotation works. Hopefully that makes sense. And yeah, that concludes all the vector functions I wanted to cover. Now we can start talking a little bit about how all these functions work from a game mechanics point of view. Now, I don't have time to go in depth on every possible use of a vector in a game because there's infinite. Vectors are so incredibly useful. But I will go through a few really common uses for vectors in 3D games. So for example, let's say I have two positions, one position here and one position here. And of course I have my giant 2D or 3D coordinate system. I can treat these positions like vectors. So the point is where the vector ends. Now, why would I want to do this? One of the most common things is, let's say this object, I'll call it object A, is my player. And this object, I'll call it object B, is my enemy. And I want my player to go directly at the enemy, just straight down this line, and go right at him for some reason. I don't know. How on earth would I do that? Vectors make this incredibly easy, because all I have to do is vector subtraction. If I treat these as vectors, A minus B, if I say that's vector C, then vector C not only gives me this direction, the direction between them, but the length of vector C is the distance between them. I get distance and direction in one incredibly easy calculation. That has to be the #1 use of vectors. It's also my favorite use. I love using vectors for this. If you ever want to figure out, hey, what direction between two things? Subtract them. Boom. There's the vector between them. And yeah, definitely my favorite use of vectors. I love using vectors like that. Another thing I really love using vectors for is just easily getting trigonometric functions because, cosine and sine, yeah, they're useful. They're just, not very fun to calculate, are they? But vectors make them incredibly easy. If I won't have, let's say, well, really anything. If I have some angle, want to find the cosine of this angle, easy way, just create a vector like this, call it vector A, then take my x-axis, call it vector B, and do A dot B. Has to be my favorite use of the dot product because as long as A and B are of normalized length, so I'll have to normalize these first, but that will get me effectively how did I draw a line there? Anyways, it'll get me the cosine of whatever that angle is. I easily get the cosine as long as A and B are normalized. Definitely my favorite use of the dot product. It's so much fun. If I want sine, I can do the same type of thing with the cross product. I'll do A cross B, make sure these are normalized, so make sure those are normalized, and then that gets me the sine multiplied by whatever this in vector is, whatever the perpendicular vector is. But if I don't care about that vector, then I just take the absolute value of this. So really, if I take the absolute value of it, then there you go. I get the sine. Well, absolute value is equivalent to vector length, in case you didn't pick that up by now. Yeah, that gets me the sine of it. So another incredibly awesome use of that. So those were probably my favorite uses of vectors right there. Just finding distance between two things and getting easy sine and cosine of angles between things. If you do things with vectors, all that stuff is just, it's so easy. And in fact, here's a pretty common game problem that I'll go through right now with you. Let's say I have some square. And what I want to know is I want to know what direction the square is facing. What direction is up on this square? If I remotely draw it up, we're facing. Yeah. How do I find the up direction? Here's how you solve it. First off, just take 3 points, any 3 points. I'm going to take these three, A, B, and C. What I'm going to do is I'm going to take A minus, wait, I'm doing it backwards. Actually, wait, it doesn't even matter, does it? Whatever, I'll do it that way anyways, because that's the way I'm used to. So A minus B and C minus A. That gets me two vectors. I'll call them Q and R. Why not? You can call them anything you want. So this gets me vector Q and vector R. But the cool thing is, these vectors, Q and R, are perfectly aligned with these lines right here. And what do I want? I want some vector that's perpendicular to those lines. So guess what I do? Q cross R, cross product. And that gets me that vector right there. So there you go. Those are just a few different ways you can use vectors. And again, there's so many ways to use vectors. Vectors are such an awesome tool for game development, but yeah. So I just wanted to show you a few different ways you can use them. And yeah, that's really everything I want to cover in this companion video about vectors. So thank you, hope you enjoyed, hope you learned, and feel free to play around with vectors. It's so much fun once you know what you're doing. But anyways, thank you, see you next time.